So let us start the lecture. We continue with the examples of inner product space and Hilbert spaces. So let's take one more example. Let x be equal to the set of continuous functions on some closed interval a b. Okay, then we know that x is a complete normal linear space with respect to the norm. This is the norm here. Norm of f is equal to the supremum a lesser equal to x lesser equal to b, means x lies in the closed interval a b of f of x. Okay, but this same space CAB is not complete, is not complete normal linear space with respect to the norm. That's called the integral norm. Okay, with respect to this norm f2, it's equal to integral a to b mod of f of t square dt whole power 1 by 2. That's the Riemann integral. Okay, so this you had done. This is complete with respect to the sup norm, but it's not complete with respect to the integral norm. But however, we'll see that it's an inner product space if we define the inner product in a way that the norm induced by that inner product will be this norm 2. Okay, तो हम इसमें एक ऐसा इनर प्रोडक्ट डिफाइन करेंगे, उस इनर प्रोडक्ट से जो नॉर्म डिफाइन होगा, जो इंड्यूस होगा, वो ये नॉर्म होगा, सेकंड वाला. दिस इज द फर्स्ट नॉर्म, दिस इज द सेकंड नॉर्म. ओके, दिस इज द फर्स्ट नॉर्म, दैट्स सेकंड नॉर्म. So that means this x equal to CB, it's an inner product space with respect to that inner product, but it's not a Hilbert space, because with respect to this norm 2, it's not complete actually. However, we will also see that there is this norm, the norm 1, which we have defined above. This norm is not induced by inner product. So with respect to norm 1, so we don't have any inner product. We don't have any inner product which induces this norm 1. We have inner product which induces norm 2, but with respect to norm 2, it's not complete. With respect to norm 1, it's complete, but we don't have any inner product which induces norm 1. So that means we can say that it's not Hilbert space with respect to this. Now it's not inner product with respect to if you want to define inner product so that it will become complete, so that's very difficult. So but we have a completion of this space, that's called L2 space, capital L2 space. It's a Lebesgue space, Lebesgue integrable, square integrable functions that we'll discuss later on. So let's first see that we have an inner product which induces norm 2. So now define this function on CAB by, let's see this function. It's f of, you can write f of t g of t conjugate dt, and it's a to b integral. Okay, and obviously it's a scalar number. Integral of f t g t, it's obviously a scalar number, positive or negative. So this is a function from CAB cross CAB to R, or you can see complex numbers, or in fact if we take complex valued functions also, so that's why there is a conjugate. Okay, so conjugate means when we take the functions from closed interval AB to complex numbers to C, complex plane. So let's check that the inner product properties of this function that we have defined here. So first property is this thing, inner product f with f. So this is equal to integral a to b f of t conjugate dt, that's equal to inner product a to b, its mod of f of t square dt, which is always greater or equal to 0. It's always greater or equal to 0. Okay, so this is true for all f in CAB, continuous functions. Okay, and one more thing, this inner product is 0 if and only because this inner product is equal to that integral that we have here, if and only if the integral mod of f of t square dt is equal to 0. But since f is continuous and it's a non-negative function, the integral of a continuous non-negative function is equal to 0 if and only if the function is 0. Okay, so continuity is very important here. F is also continuous here, so that means f of t square, okay, mod in fact is 0. This is true if and only if f of t is equal to 0. In fact, it's true for all t, okay, which is in this interval a b. So that means f of t is equal to 0 for all t belongs to the interval a b. So which means that this is true if and only if f is equal to 0. So that's the first property. Now we verify the second property. So what's second property? It should be conjugate, symmetric conjugate. Okay, so this one. So for this, let's take two functions in CAB. Then you can see this by definition is equal to AB f of t g of t conjugate dt. So this is equal to a to b f of t conjugate g of t dt whole conjugate. So because we know that integral conjugate of integral is equal to integral of conjugate. Okay, conjugate को हम इंटीग्रल से बाहर निकाल सकते हैं, तो ये इंटीग्रल पर कंजुगेट है उसको हम इंटीग्रल के अंदर ला सकते हैं. तो वहाँ पर एफ टी कंजुगेट होल कंजुगेट वो एफ टी के बराबर आ जाएगा जी एफ टी कंजुगेट. तो इसे that's equal to a to b. It's right here is g of t f of t conjugate dt whole conjugate. So this is what's this? This is inner product gf with whole conjugate. Next property, that's additive property. The linear property, you can say let f g h belongs to c a b and alpha is any scalar. Then now let's first check this. F plus g with h is equal to, you can easily verify this is the property of Riemann integration actually, and g of t conjugate dt. So that's equal to a to b. Now the addition is the pointwise. It is f of t plus g of t, okay, whole conjugate, and here, sorry, it's not conjugate here, so we don't have conjugate here. So f of t plus g of t, here it's h of t conjugate, okay, here it's h of t in the first line, okay, this is h of t conjugate, okay, not g of t. So this is h of t conjugate dt. Now they are just the numbers in the field. Okay, so we can apply the distributive law here. This is a to b f of t h of t conjugate plus g of t h of t conjugate. Now we are in the Riemann integration. Integral of f plus g is equal to integral of f plus integral of g. It's equal to a to b f of t h of t conjugate plus integral a to b g of t h of t conjugate. So let's write here dt dt, and this is clearly, this is by definition, it is the inner product of f with h plus inner product of g with h. And let's check one more property of linearity, that's alpha. Okay, alpha times f, and integral alpha f, this inner product alpha f g, that's by definition is equal to a to b alpha f of t and g of t conjugate dt. And the scalar multiplication is again point wise, so it's equal to alpha times f of t g of t conjugate dt. अल्फा को हम इंटीग्रल से, इट्स अ स्केलर, the property of Riemann integration. dt. Okay, so this is f of fg. So therefore this is an, so sorry, this is an inner product, and therefore this is an inner product, inner product on CAB, right? So but the norm induced by this inner product, let's see the norm. The norm induced by the inner product of this is given by norm of f2, that's equal to inner product of f power 1 by 2 square root. That's equal to, what's the inner product? This is the integral a to b f of t conjugate dt, and that's equal to a to b mod of f of t square dt. And this CIB is not complete with respect, and CIB is not complete, and CIB is not, it's not complete with respect to the norm, this. Okay, so therefore this CAB is not Hilbert space. Therefore CAB is an inner product space but not Hilbert space. Therefore CAB is an inner product space, but not Hilbert space. Okay, it's not Hilbert space. Okay, so Hilbert space and its inner product space with respect to this inner product. Next, we show that the norm which is equal to supremum of mod of f of t where a lesser equal to x lesser equal to b, this on CAB is not induced by inner product. Okay, is not induced by inner product. So take this here, take x equal to this particular case हम लेंगे, it is not in general. Let's take this closed interval. So for if the norm, which is called supremum 0 lesser equal to x lesser equal to 1, let's say here it's t. Okay, ऊपर यहाँ पर आप चलिए x लिख दीजिए, it's f of x. Okay, for this norm where f is in this C01 is induced by an inner product. Suppose ये किसी inner product से induce होगा, then it must satisfy parallelogram law. Then it must satisfy the parallelogram law. Okay, then it must satisfy the parallelogram law. So that law means norm of f plus g whole square plus norm of f minus g whole square must be equal to what? That must be equal to this twice norm f. So that's so therefore we must have this. Therefore norm of f plus g whole square plus norm of f minus g whole square must be equal to twice norm of f whole square plus norm of g whole square. This should be hold for each f g belongs to this piece. अगर ये parallelogram law satisfy करेगा, so this should satisfy. Okay, so let's take two functions. Take f of x equal to x and g of x is equal to 1 in this interval C01. So obviously the supremum norm of f is 1 because the supremum of f of x over the interval 0 1 is 1, and supremum of g is also 1 because it is a constant function. So then norm of f, let's write this norm of f, and then norm of f which is equal to the supremum of f of x, so 0 lesser equal to x lesser equal to 1, which is equal to supremum of mod of x where 0 lesser equal to x lesser equal to 1, obviously this is 1, and norm of g which is the supremum of g of x with 0 lesser equal to x lesser equal to 1, that's equal to the supremum of the 1, which is constant here, 0 lesser equal to x lesser equal to 1, that's equal to 1. So both are 1. So now let's calculate supremum of f plus g, norm of f plus g and norm of f minus g. Now norm of f plus g, what's this? This is a supremum of fx plus gx, actually f plus g of x, but the addition is component wise here. Let's skip that stuff here. Okay, this is equal to supremum. What's fx? That's x, and what is gx? It's 1. So it's x plus 1. It's a supremum of x plus 1 is 0 lesser equal to x lesser equal to 1. Obviously this supremum is 2, so the maximum value is 2. And let's find this norm of f minus g. So this is equal to, you can easily calculate it, it's 0 lesser equal to x lesser equal to 1, fx minus gx, that's x minus 1. What's the supremum of this? If x x's value is 0, then the value is 1, and if the value of x is greater than 0, then obviously value is less than 1, so therefore supremum is 1. So thus we have this norm of f plus g whole square plus norm of f minus g whole square, it's equal to norm of f plus g is 2, it's 2 square plus 1, that's 5, and
जीरो मतलब सुप्रीम
no सुप्रीमम 0 नहीं आएगा, सुप्रीमम इसका 1 आ जाएगा f माइनस जी का। आप x के वैल्यूज को वेरी करोगे, सो x का वैल्यू अगर 0 आप लोगे उस टाइम में इसका वैल्यू जो होगा वो 1 होगा, और x का वैल्यू अगर आप 1
ले सकते हैं सर हम।
यस
सर 1 भी ले सकते हैं।
हाँ 1 भी दिस, बट यू हैव टू फाइंड द सुप्रीमम वैल्यू ऑफ दिस। आपको सुप्रीमम वैल्यू करने का, मैक्सिमम वैल्यू। अगर आप x को वेरी करते रहोगे ना 0 से लेकर 1 तक, इस x माइनस 1 का आपको मैक्सिमम वैल्यू चूज करना है, राइट? हाँ क्लियर हो गया ये पॉइंट?
यस सर।
ओके, तो आपको इस फंक्शन की तरफ देखना है कि इसका मैक्सिमम वैल्यू क्या है, सुप्रीमम वैल्यू इसका क्या है। ओके, सो एंड so thus this is equal to this one, it's equal to 4, it's equal to 5, and twice let's calculate this norm of f whole square plus norm of g whole square. So both the values are equal to 1, that we have already calculated it, it's 1 plus 1, that's equal to 4. So that 4 is not equal to 5, therefore this sum of the norm is not equal to this. So therefore norm of f plus g whole square plus norm of f minus g whole square is not equal to twice norm of f whole square plus norm of g whole square. So thus this norm is not induced by inner product. अगर ये इंड्यूस होता ना इनर प्रोडक्ट, देन इन दैट केस इट विल बी हिल्बर्ट स्पेस विथ रिस्पेक्ट टू दिस इनर प्रोडक्ट, दैट इनर प्रोडक्ट अगर इंड्यूस होता है इनर, बट इट्स नॉट इंड्यूस्ड बाय इनर प्रोडक्ट, सो वी कैन नॉट टॉक अबाउट दिस इट्स हिल्बर्ट और इट्स इनर प्रोडक्ट स्पेस. So we have seen that this CAB it's not Hilbert space, okay, with respect to the integral norm, and it's also not inner product space, okay. It's not a the supremum norm is not induced by inner product, that we already also see.
सर हम g की नॉर्म 1 क्यों लेते हैं?
G is a constant function, okay. Let's see that what's g of x is 1, okay, throughout 1. So what will be the supremum of g of x? Let's see the last line, the supremum of 1. अब x के it's independent of x है ना, इसका वैल्यू हमेशा 1 ही आ जाएगा. So the supremum
हमने फिक्स किया है यहाँ से.
हाँ ये it's g is constant function, g is a constant function.
ठीक है ठीक.
So our next topic is the orthonormal sets. Okay, orthonormal sets. ऑर्थोनॉर्मल सेट्स, यहाँ तक सब क्लियर हो गया? ये एग्जांपल्स जो भी हमने ली है.
यस.
ओके, सो लेट्स नाउ डिस्कस ऑर्थोनॉर्मल सेट्स. So again this topic is from Lemay. So in fact this unit, ये जो सारा यूनिट है ना थर्ड आपका, it's you can see it's from page number 369 to, in fact it's from page number 367, okay, 367 to 401 जो भी इसमें है लेमाई में, इस पेज नंबर से लेकर 401 तक ये आपका यूनिट थर्ड है. ऑर्थोनॉर्मल सेट्स. So what's orthogonality actually? So we know that in R2 this if the vectors are perpendicular to each other, if their dot product is 0, है ना, that you know. R2 में अगर आपके पास दो वेक्टर्स होगी, उनका अगर डॉट प्रोडक्ट 0 के बराबर होगा, then we say that these two vectors are perpendicular to each other. And what's actually inner product? It's actually the generalization of dot product on R2. So in general we define orthogonality, orthogonal vectors in inner product spaces, orthogonal. So in case of R2 is respect to dot product, we call the vectors are perpendicular to each other, but in general setting we see the vectors are orthogonal to each other. So we introduce orthogonality in general inner product space actually. So like we have two vectors, say 0, 1 and 1, 0. They are orthogonal in these two vectors. Let's see these two. So we can see this. So this is 0, 1 means 1, 0 means this vector. Okay, so this one, and 0, 1 means this one. So this is 0, 1. So they are orthogonal to each other. You can calculate their dot product, that's equal to 0. So two vectors are orthogonal if their dot product is 0 in R2. And we now introduce the orthogonality in a general inner product space, in general linear space actually, where inner product is defined. So let's start with these two vectors. In R2 are perpendicular if their dot product is 0. If their dot product is 0. Now the inner product is a generalization of dot product on R2, since inner product is the generalization of dot product on R2. डॉट प्रोडक्ट इट्स वन ऑफ द इनर प्रोडक्ट ऑन R2. आप और बहुत सारी इनर प्रोडक्ट्स को डिफाइन कर सकते हो ऑन R2 अदर देन दिस डॉट प्रोडक्ट. सो दिस इज द पर्टिकुलर example of inner product, that's dot product. Okay, so since the inner product is a generalization of dot product on R2, so what we can do, so we can introduce the concept of and that inner product is defined on any linear space, okay, not on only R2. So we can introduce the concept of perpendicularity. Perpendicularity for elements of X. For elements of any inner product space, okay, inner product space X as follows. So let's start this. Let X be an inner product space. Inner product space, and we say that X and Y are orthogonal if their inner product is 0. Okay, X and Y in X, we say that X and Y in X are orthogonal if their dot product is equal to 0. And we also introduce notation here, that's we call the per. Okay, and in that case we write we write X per Y. So that's X per Y. X is if the inner product is 0. So that's x per y if inner product is 0. अगर inner product 0 होगा तो we can use this notation actually. Now when we say two subsets of x are orthogonal to each other, so if we have two subsets of x, okay, if E and F are subsets of x, we say we write, sorry, not we say, we write E per F, so it's F here, means E is orthogonal to F actually. We write this E per F, okay, we write E per F if x per y for all x in E and y in F, okay. अगर E का हर कोई वेक्टर ऑर्थोगोनल होगा F के हर किसी वेक्टर के साथ, so then we say E per F, okay. This is the notation E per F. So it means that, so that's every element of E is orthogonal to every element of F. That is every element of E is orthogonal to every element of F. Every element of F. And when we say that the subset is orthogonal, okay, we say that E is orthogonal, is orthogonal if any two vectors of E are orthogonal to each other. If x per y for all x, y and E, in words we can say that is every vector, every element or every vector of E is orthogonal to every vector of E. Okay. So that's the definition of orthogonal set. Now let's define the normal vector, okay, or when we see that the set is orthonormal, okay. An orthogonal subset and orthogonal subset. First it should be orthogonal, okay. Orthogonal subset E of x is said to be orthonormal if inner product of x with x, this inner product, or you can say the norm of x. In fact, norm of x, it is a square root of this if this is equal to 1. If the norm of every vector in this set is equal to 1, or the inner product of x with x is equal to 1, because it is a positive square root. So this also means this inner product of x with x is 1. If the inner product of any two different vectors is 0 and the inner product of x with itself is 1, then we see that set is orthonormal. So orthogonal means the inner product of any two different vectors is 0, that's orthogonal. Orthonormal means inner product of the vector with itself is equal to 1. So that's actually the norm. The length of the vector is 1, okay, orthonormal. So clearly if E is orthonormal, then 0 is not in E. Clearly, this is clear, okay. Clearly, if E is orthogonal में 0 हो सकता है, okay, but orthonormal में 0 clearly is orthonormal, okay, not orthogonal, orthonormal, orthonormal, then 0 is not in E, because if 0 is in E, क्योंकि ऑर्थोनॉर्मल की डेफिनेशन क्या है, नॉर्म ऑफ एनी वेक्टर should be equal to 1, so norm of 0 भी 1 के बराबर होना चाहिए, which is not the case. This is not the case, okay, this is not true. Norm of 0 is not equal to 1. So this is the reason. And orthogonal set, but
सर हम बेसिस वेक्टर लेंगे, बेस वेक्टर.
okay, वो हम डिस्कस करेंगे आगे. But orthogonal set may contain zero vector, may contain zero vector. In fact, we can say that zero vector is orthogonal to each vector. In fact, zero vector is orthogonal to each vector of x. So अब आप बेसिस की बात कर रहे हैं, तो बेसिस में सबसे पहले इट शुड बी लीनियरली इंडिपेंडेंट, है ना, बेसिस का सेट. हम ये चेक करेंगे जो भी ऑर्थोगोनल सेट होगा, अगर उसमें जीरो नहीं होगा ऑर्थोगोनल सेट, क्योंकि ऑर्थोगोनल सेट में जीरो भी हो सकता है ना, जीरो में बिलोंग टू ऑर्थोगोनल सेट. बट अगर आपके पास गिवन ऑर्थोगोनल सेट है, उसमें अगर सपोज जीरो वेक्टर, उसको आप बाहर निकालें, या अगर नहीं होगा तो फिर आपको बाहर निकालने की जरूरत नहीं है. सो लेट्स टेक ऑर्थोगोनल सेट विदाउट जीरो, ओके, देन दैट ऑर्थोगोनल सेट इज ऑलवेज लीनियरली इंडिपेंडेंट. बट वो बेसिस बनाए या ना बनाए हम उसके बारे में नहीं कह सकते, बट that's always linearly independent. अब एक्चुअली कन्वर्स आप कह रहे हो कि अगर आपके पास कोई बेसिस होगा, हम जनरल रिजल्ट प्रूव करेंगे अगर हमारे पास कोई भी लीनियर इंडिपेंडेंट सेट होगा, वो इन पर्टिकुलर बेसिस के लिए भी ट्रू होगा, क्योंकि बेसिस का जो सेट होता है वो लीनियरली इंडिपेंडेंट होता है. तो कोई भी लीनियरली इंडिपेंडेंट सेट अगर होगा, वो जरूरी नहीं कि वो ऑर्थोगोनल होगा, इट्स नॉट नेसेसरी. हम एग्जांपल्स दे सकते हैं लीनियरली इंडिपेंडेंट सेट्स की विच आर नॉट ऑर्थोगोनल, बट व्हाट वी कैन डू, we can produce a new set of vectors from that linear independent set, such that the new set of vectors will be orthonormal, but the span of both the sets will be same, the given linearly independent set and the new set of vectors जो कि अब orthonormal है, दोनों का span सेम होगा, दोनों सेम स्पेस को जनरेट करेंगे. सो बेसिस का जो सेट होगा, इट्स नॉट इन जनरल, it's not orthonormal, they are not orthogonal vectors. We can give any number of examples. So in particular, let's take this R3 space, okay, and let's take these set of vectors. So 1 1 1, let's take 0 1 0, and let's take 0 0 1. So these three vectors are, I think, they are linearly independent. You can check 1 1 1, this determinant must be equal to non-zero. So if the determinant is non-zero, then these vectors are linearly independent. So obviously they will form a basis for R3, because the dimension of R3 is 3. So maximal linearly independent set will be the basis. So if they are linearly independent, then this will be the maximum linearly independent set, because it can't have 4 linearly independent vectors, as the dimension of R3 is 3. So let's see this. So this is obviously 1, which is not equal to 0. So that means these set of vectors, this is linear, it's a basis. So this means this set is a basis. ये एक basis है इस R3 की, ठीक है. R3 की बहुत सारी basis हो सकती है, but this is not, they are not orthogonal. These two are orthogonal, but this is not orthogonal to these first two vectors. You can see that our product. So that's obviously 1, which is not equal to 0. So this set is not orthogonal. In fact, it's also not normal भी नहीं है इनके vectors. Normal तो अगर आप इसका norm निकालोगे, so that's obviously √3, I think. इन दो का norm तो 1 आ ही जाएगा, but the first vector its norm is root 3. Okay, so bases need not be orthonormal or orthogonally defined bases. But if you take the standard basis here, so that if I take the first vector 1 0 0 instead of 1 1 1, then that is also a basis, but that set is also orthonormal. वो set orthonormal भी होगा और basis भी होगा, but in general basis need not be orthonormal. That's an example. मगर अब हम क्या कर सकते हैं इसमें, मतलब आगे आपके पास ये जो सेट है, दिस इज सेट ऑफ लीनियरली इंडिपेंडेंट वेक्टर्स, इसका जो स्पान है दैट्स R3. ओके, इससे पूरा R3 जनरेट हो इन तीन वेक्टर से, but these three vectors they are not orthonormal, but we can construct a new set of three vectors, say u1 u2 and u3, such that this set of vectors is orthonormal and the span of u1 u2 u3 is same as the span of these three vectors. So both generate the same space. That's a theorem, that's called the Gram-Schmidt process, which we do in coming lectures. So let's first check some properties of this orthogonal set. So first we do the following theorem that we called the Pythagorean theorem for in the inner product space. So let's state this theorem. Let X be an inner product space an inner product space. Okay, and we have suppose orthogonal set, we have suppose perpendicular vectors here, and let this is called the Pythagorean theorem actually for the inner product space. Pythagorean theorem, Pythagorean. Let x1 x2 up to xn, they are suppose orthogonal vectors, it's an orthogonal set, Bn orthogonal set, then norm x1 plus x2 plus xn its square is equal to norm of x1 square plus norm of x2 square plus norm of xn square. Yes. So proof is very simple. So you start with this, you start with this, you can see this is equal to norm x1 square plus norm x2 square. So let's start with this. First we write this. We have this inner product xi xj is equal to 0 for all I j runs from 1 to n, but I not equal to j, because it is an orthogonal set. So inner product of any two vectors is any two different vectors, okay, two distinct vectors, it's always equal to 0 as the set is orthogonal. Now let's find out the norm of x1 plus x2 plus xn square. This is by definition, it's the inner product of the vector with itself, x1 plus x2 plus xn, then x1 plus x2 plus xn, and if you expand it, it's inner product of x1 inner product of x2 with x2, and plus the other inner product of x1 with x2 वो भी आ जाएगा, but that's equal to 0. It's equal to inner product of x1 with x1 प्लस इनर प्रोडक्ट ऑफ एक, तो ये सारी आ जाएगी इसमें. मैं सिर्फ डायगोनल एंट्रीज लूँगा फर्स्ट, then I take the non-diagonal entries which are obviously equal to 0, plus I will take this summation inner product xi xj ij runs from 1 to n but I is not equal to g प्लस ये टर्म्स आ जाएगी मतलब इनर प्रोडक्ट ऑफ x1 with x2 इनर प्रोडक्ट ऑफ x1 with x3 इनर प्रोडक्ट ऑफ x1 with xn देन इनर प्रोडक्ट ऑफ x2 with x1 x2 with x3 क्योंकि x2 with x2 वो मैंने ऑलरेडी लिया है तो ये जो इनर प्रोडक्ट से ये सारी जीरो के बराबर है दिस इज इक्वल टू inner product of x1 with x1 plus inner product of x2 with x2 plus inner product of xn with xn plus 0 okay but this one that's equal to norm x1 square plus norm x2 square plus norm xn square so that's we have this norm of x1 plus x2 plus xn square is equal to norm of x1 square plus norm of x2 square plus norm of xn square. So that proves this Pythagoras theorem. So any question?